The purpose of this lab was to examine a video of two pool balls colliding in Tracker and model the data in Python to see if the momentum principle was satisfied. The conclusion was that though the momentum principle is ideally satisfied in Python, as shown in the energy graphs, in reality, there is never a perfect elastic collision, and energy is lost during the collision due to external forces such as drag force and the force of friction. Collisions are very difficult and almost impossible to model in Python, but an ideal situation can be modeled to show a ball moving at an initial velocity, transferring all momentum to a ball at rest it collides with. To do this, a ball is shown moving and hitting another ball and losing all its energy. The ball at rest receives all of its energy and moves in the same velocity that ball 1 was finally moving at. A video on YouTube was found of two pool balls colliding, one initially at rest and one moving with an initial velocity of negative 1.7 meters per second. The video was imported into Tracker to be further analyzed. An XY axis was added to plot the data, and a calibration stick was added as the diameter of one of the pool balls, with a diameter of 0.0615 meters. The point masses were then calculated for each ball and saved in a CSV file to be iterated through later. In the Python code, the data was iterated through and modified to move in the positive x direction. A partial code was initially found and built upon, adding energy principles, Newton's second law, and conservation of momentum principles. The initial conditions were inputted. Both average masses of a pool ball are 0.15 kilograms, and the initial velocity of ball 2 was 0, and ball 1 was 1.7 meters per second modified. And the initial masses are here, and a very, very small time step was used to get more precise data. The collision was then predicted in an ideal scenario. To do so, a while loop was created, and with each iteration, the new position, velocity, and momentum were calculated. Newton's second law was used to calculate the new position, using the formula final position equals initial position plus change in velocity times delta t. The new velocity was then added using the final velocity equals the initial velocity plus F net times delta t, where F net equals the change in momentum over change in time. The new momentum was then calculated with the new velocity using P final equals mass times velocity. The energy principles were also used to calculate the change in energy and then plotted in a graph to examine and see if the momentum principle was satisfied. So, the initial kinetic energy and potential energy was found of the system, and then the change in energies were found and then plotted in this graph. In an elastic collision, the change in kinetic energy should be 0 since the final kinetic energy equals the initial kinetic energy. With that in mind, in each iteration, the new kinetic energy was found using the formula Ke equals half the mass times velocity squared, and the change was plotted and shown to be 0. Though the graphs show that ideally the change in energy is 0, in actuality, there is some loss in energy, so the change in energy graph would be some negative number. This shows that in reality there was always some external force, like the force of friction, drag force, etc., that causes the momentum principle to be mostly satisfied, but that some energy will be lost during this collision. So the momentum principle in an ideal situation will show that energy is conserved, which means that the energy of the system does not change, and the final energy equals the initial energy. So what does this mean? With these principles in mind, the force needed to hit any pool ball into a socket can be calculated. The velocity that the white pool ball needs to hit the other pool ball into the socket can be calculated using distances on the pool table and basic geometry, and the equation velocity equals change in distance over change in time. With this information, the force can be calculated using the data that using the idea that every action has an equal and opposite reaction, or force times time equals the final momentum, or mass times the velocity calculated. By implementing the conservation of momentum principle, one can win almost any game of pool.